we had to begin. So, and good afternoon, good morning, everyone. So for Jim, it's good afternoon. Yeah. Hello, everyone. Welcome to today's Future Ocean Forum. And I'm Zhiwei Zhang, supervisor in the Academy of Future Ocean, Ocean University of China. And I will host today's webinar. Today is our great honor to invite Professor James McWilliams from UCLA to give us a nice talk. Before the formal beginning, I would like to take a moment to briefly introduce Professor James McWilliams. So James McWilliams received his college degrees in applied mathematics, very strong skills in mathematics for James, including a bachelor's degree with honors in 1968 from Caltech, and a master's degree in 1969, and a PhD in 1971 from Harvard University. After holding a research fellowship in geophysical fluid dynamics at Harvard, he jointly established the Oceanography Section at the NCAR, where he became a senior scientist in 1980, nearly 45 years ago. In 1994, he became the Louis Slichter Professor of Earth Science in the Department of the Atmosphere and Ocean Science at the UCLA. Jim is a AGU Fellow and also a member of the United States National Academy of Science. For Chinese, it is 中国科学院院士，美国科学院院士 the member of the United States National Academy of Science. So James' research focuses on the fluid dynamics of the Earth's ocean and atmosphere. I think many of us are very familiar with James' work. He has done many outstanding works in our field. For example, for several examples, the GM parameter transitions, the KPP parameter transitions, and the semi-scale theories, many, such as the turbulent thermal winds and the frontogenesis, many, and so on. He is also a co-creator of the Regional Ocean Modeling System, the ROMS. The ROMS is a widely used OGCM. I believe many of us have used it or are still using it now in the numerical simulation. So the title today of his talk today is the mean bottom slope current in the ocean. I think it's the new works in his groups. So okay, now let's welcome Professor James McWilliams to give us the talk. Okay, James, Professor Yang, you can stop the screen share. 姜老师，你可以停止共享屏幕。Okay, Jim, you can share your screen.
Okay, thank you for the introduction. Can you see the screen?
Yes, we can see the screen. Yeah.
Good. Today I'm talking about the time averaged currents at the bottom of the ocean, in particular over topographic slopes, which is most everywhere. This work has spread over several papers and several years, and I am listing my primary collaborators here. This talk is both an overview of a particular dynamical phenomenon called topostrophy, which I will define, and it's an analysis of the time mean bottom currents over much of the world's ocean in 3 separate basins, the Atlantic, the Pacific, and the Indian, as you see here with the bottom topography. The topography, of course, is quite complex, continental slopes, mid-ocean ridges, fault lines, deep canyons, deep trenches, and it is in all these places that I want to talk about the time mean circulation. The primary basis for what I will say today is the three simulations that I described using the Regional Oceanic Modeling System under realistic forcing and topography conditions, and with what we call hyper mesoscale grid resolution, that is horizontal grid scale of 6 kilometers and high vertical resolution. These are fully tidal solutions. The deep ocean has few measurements. More often they're hydrographic measurements than velocity measurements. And most often they don't have good time averages. And so on the whole, this deep region is little measured. Global oceanic simulation models have often had limited horizontal resolution for mesoscale eddies, and usually had coarse vertical resolution below the picnic line, as well as an incomplete representation of the bottom boundary layer. And all of these limitations limit the depiction of the time mean bottom currents. And so the question being addressed today is, what are these abyssal currents, in particular right at the bottom? The starting point for this story is called topographic turbulence theory, and it had a marvelous year of simultaneous discovery by 3 different groups listed here. And although they gave very different interpretations, they all came up with the same result, that random barotropic eddies above random topography evolve towards a mean circulation aligned with topographic contours. Because they were doing essentially an idealized horizontally periodic problem, the random topography gave the answer of anticyclones above hills, cyclones above valleys, and they gave it various interpretations. Entropy minimization associated with the 2-dimensional turbulence cascade of vorticity squared, that is entropy towards small scales and dissipation. Entropy maximization, that is, what is the most probable state given for a given kinetic energy in a domain, or turbulence closure theory. At this period now, almost really 50 years later, most people would sort of combine these into describing this as mesoscale eddy mixing of potential vorticity with this outcome. For realistic oceanic basins, it's not random hills and valleys, but the primary slopes are continental slopes, ridges, and seamounts. And the expression of this answer is what's called prograde flow along isobaths. Prograde means in the direction of topographic Rossby wave propagation. There was a period of time this was called Neptune, and the more modern term, and the one I use, is topostrophy. And for nearly 50 years, the question has been, how might this dynamical behavior occur in a 3-dimensional baroclinic non-geostrophic flow? And from a theoretical point of view, it is sort of a subtle question, because topographic variations only appear in the bottom boundary condition, not the interior fluid dynamical equations. That is, the interior potential vorticity, which I just mentioned, has no direct awareness of local awareness of the topography in the interior. The evidence, observational or modeling for its occurrence, is not particularly strong, although there have been some deep current meter analyses I list two here that suggest that apostrophe might often occur. Only recently has the model resolution become good enough where simulations can show that topostrophe is the dominant cause of deep mean flows, and mesoscale eddies cause it with a finite vertical penetration scale of hundreds or thousands of meters above the bottom, controlled by the stratification and rotation. Furthermore, under a topostrophic flow, the bottom boundary layer typically causes a turning of the mean flow cross slope downhill as the most common time mean component. So just to define terms in this slide, I'm talking about bottom currents. The subscript B means bottom. I'm talking about topographic gradients. H is the resting depth. When I have a perpendicular symbol next to a vector, I mean the horizontal component. And so prograde along slope flow, that is flow along isobaths in the direction of topographic Rossby waves, is defined here as UP. The cross slope flow perpendicular to the topographic gradient, or excuse me, parallel to the topographic gradient, is defined here as UC, and positive UP is prograde flow, positive UC is uphill flow, and thirdly, the vertical velocity, which is positive upward. Two of these components are closely related through the kinematic bottom boundary condition of no normal flow, and so we can alternatively talk about the cross slope flow or the vertical flow. So just to give you a visual sense of what we're talking about, in addition to the theories of wind and thermohaline driven deep boundary currents, which are present in the solutions I'm talking about, but actually not the primary currents, there are three sort of modern conceptions of what the abyssal bottom current should be. One is the topostrophic conception, which I just talked about, in which you see the cartoon there. If it makes a mean flow along the isobaths, it's caused by mesoscale eddies in the ocean, and the cross slope flow is downhill near the boundary in the bottom boundary layer and uphill above. A second conception, which has been fairly popular in recent years with many papers, is mixing driven boundary layers. And here the conception is that if you have stratification near a slope and you have turbulent diapycnal mixing, then you will tend to make a uphill flow near the bottom, a downhill flow above it, and the along slope flow will be weak and actually opposite to prograde, as indicated here by the symbols. A lot of the motivation for a mixing-driven bottom boundary layer is modern microstructure measurements of enhanced turbulence in the deep ocean, particularly near topography. And if you didn't otherwise have a mean circulation, this might indeed be the outcome. Finally, we've understood for a long time, at least in models, that if there is a flow across a ridge or a canyon, then it will be above a ridge, uphill on the upstream side, downhill downstream, and the canyon flows will be the opposite. So, given these ideas, what is it that we see in realistic simulations with high mesoscale eddy resolution and careful parameterization of the bottom boundary layer. I first will show some results from the Mediterranean Sea. This is part of the published paper listed here. And what you see along the slope, which is south of Spain, that if you time average and average along the along the slope, you will see that the stratification bends towards being perpendicular to the slope in the bottom boundary layer. This is an expression of there being no buoyancy flux through the bottom, but the along slope flow, which is what's colored here, is topostrophic, and it's most intense near the bottom, but it extends vertically many hundreds of meters, and it is a very simple dominant pattern of topostrophy. If you look at the vertical velocity in the cross slope plane, what you see is that in the bottom boundary layer it is downhill, and above it is uphill. This is a very simple result, but if you actually look in the structure along the slope, you see this picture, which is that the topostrophic flow is non-uniform along the slope, but certainly predominantly positive. And if you look at the vertical velocity, then it is up and down as the flow crosses over canyons and ridges. And yet the average is the very simple pattern of, on average, downhill flow at the bottom, as you saw in the previous slide. This is a particularly clean example of topostrophic flow. Much of the world is not quite so simple as this particular sector is. So let's shift now to the 3 basin simulations that I described. And we can start with the along slope prograde flow in the Pacific. You'll notice that the pattern is rather complex, but of course so is the topography. And yet it's almost all red. And this is an honest color bar. There's just as much room for anti-topostrophic flow as there is topostrophic, and yet it is almost entirely topostrophic. Interestingly, there's an exception in the region of the South China Sea. And when one looks more globally, there are several other marginal seas where the topostrophic effect is not particularly strong. If we ask, what does it look like in the other ocean basins? Here is the Atlantic and the Indian, and it is again mostly red. So the topostrophy is very widespread. The strength of the current is stronger at higher latitudes, and it's very weak right at the equator. And this is the effect of rotation and stratification, that is, weak rotation and strong stratification near the equator, and strong rotation and weaker stratification, particularly at higher latitudes. And so the effects of the upper ocean eddies can extend deeper down into the bottom region. Again, there are some local exceptions to topostrophy. I don't know if you can see my cursor. In case you can, if you look at the wind gyre western boundary current next to the east coast of the United States in the Gulf Stream, it is not topostrophic, it is wind gyre. Similarly, if you look in the subtropical gyre in the Brazil Basin, you see that the bottom currents along Brazil, actually both southern Brazil and northern Brazil, are wind gyre anti-topostrophic currents. But still, the prevailing color is red. If we look instead at the vertical velocity at the bottom, it's a more mixed pattern, and yet it is on average blue. That is on average downhill flow, but there certainly are exceptions. And so there's certainly more going on in the bottom boundary layer than just the effect of the eddy-driven topostrophic flow. Note in particular that if you look right near continental margins, and I'm trying to find, and so for example, I'm looking across Western Americas, you see that there is a strip of uphill flow, which is certainly not consistent with the topostrophic boundary layer prediction. So the story for vertical velocity is more complicated, but still, on average, I mean, I'm asking you to see it visually here. I will show you it statistically in a moment. It is downhill bottom flow. If we shift to a more statistical view, and here we're looking at the time average statistics in all spatial locations at all bottom depths in all basins, what you see is that the PDF, first of all, it's intermittent. That is, they're long tails. You see the kurtosis values listed here for the prograde flow and the uphill flow, that is the tails, and it's skewed in the sense that downhill flow is more dominating the extreme events than is uphill flow, just as prograde flow is dominating the extreme events compared to the reverse. This is, can you still see the screen? I just hit a wrong button. Someone will tell me if they can't see the screen.
Yes, we
Yeah.
can see your screen and also
Good.
source.
This is the joint
Yes.
PDF of the along slope flow and the vertical velocity at the bottom. And you see that there is a dominance in the upper left quadrant, which is consistent with eddy-driven topostrophy and its associated bottom boundary layer. But there is another probable situation, which is along the positive x-axis, where the prograde flow is weak and the vertical velocity is upward. And in the absence of better interpretations, this, I think, is likely to be associated with mixing-driven upwelling. So both phenomena occur. Much of this mixing-driven upwelling occurs at the edges of the basins, and although I'm not explicitly showing it, it is on the continental slope, typically around depths of about 1,000 meters, as we saw in the strip of positive W near the continental edges in the previous slide. So, how can we come to a deeper understanding of eddy-driven topostrophy in a three-dimensional baroclinic ocean? The answer, as so common in the practice of geophysical fluid dynamics, is to do idealized problems in which the conditions are more controlled and the interpretation and explanation are more certain. And so in the next few slides, I'm going to show you the as yet unpublished results from an idealized problem with random eddy forcing through random surface wind curl above a simple topography that is a ridge that is uniform in one direction. This particular problem is being led by a postdoc, Yu Wei, who is a recent graduate of Hong Kong University of Science and Technology. And so what you see in this figure is the relative vorticity field at the surface normalized by F, and so it is interpretable as a local Rossby number. The Rossby numbers are not small. And so this is a strong flow that is not entirely geostrophic. On the front face of this diagram, you see a long slope flow instantaneously, and it consists of mesoscale eddies that extend down into the interior. They are surface intensified, associated with the shallow pycnocline stratification, and the fact that the forcing, the eddy generation, is near the surface. On the right face, you see a snapshot of the temperature, so approximately subtropical stratification with a shallow pycnocline. And what you see instantaneously in temperature is certainly dominated by the average stratification. So this is a strongly, these are strong eddies over strong topographic variations. The eddy kinetic energy is surface intensified, but does extend down to the bottom. The posing of this problem is statistically symmetric about the ridge top. That is, one can average both in time and in the along ridge direction. And if you do that, here are the mean currents. On the left is the prograde velocity component. Red is in the prograde direction. Blue is in the opposite direction. And what you see is bottom intensified prograde flow over the topographic slope with a compensating reverse flow over the flat part of the far field. Because of the random forcing, there is integral momentum conservation, and so there have to be both positive and negative mean flows, but the eddy-driven flow over the topography is topostrophic. You see the cross-ridge stream function on the right panel, and you see the predicted bottom boundary layer behavior of downhill flow over the topography. The dotted line is the bottom boundary layer on the mean. And so underneath the prograde flow, there is downward flow, which is then closed in the interior as this is a stream function. So the flow follows the isolines, isocolors of this flow. And the topostrophic flow is variable in strength along the, excuse me, as are the eddy strengths. And there is the reverse flow out in the flat area of this idealized ocean. Again, both are surface intensified, but they also are very tall flows that reach up into the surface layers where the eddies are strongest. If we look at a diagnosis of the eddy fluxes, this is a plot in which the color is the mean prograde flow. So it's just a repeat of what you saw on the previous slide. But the arrows are what's called the Elias and Palm flux, excuse me, which is defined here as this capital E vector, which has a horizontal component, which is the horizontal Reynolds stress. It has a vertical component that is the vertical Reynolds stress, plus this eddy temperature flux normalized by the mean temperature gradient times F. And to the extent that Reynolds stress, is a common term, then the sort of geostrophic turbulence theory and name for this second term, which is the dominant term in the vertical component, is isopycnal form stress. That is, it's pressure forces acting on isopycnal surfaces, which have very little mixing across them except in the boundary layers. And so isopycnal form stress is a vertical transfer eddy flux, a vertical transfer of momentum. The horizontal Reynolds stress is horizontal transfer. And in this flow, because it is significantly rotationally influenced, the vertical Reynolds stress is not nearly as strong as the other terms in the Elias and Palm flux. The interpretation of the Elias and Palm flux, it is a vector whose convergence in this XZ plane accelerates the mean prograde flow. And so what you see is that in the upper ocean, where the eddies are strongest, there is the Reynolds stress convergence that is the topostrophic forcing. And then there is isopycnal form stress that conveys that eddy influence down to the bottom, where you have the topostrophic flow near the bottom. And again, you see a sort of reverse pattern away from the topography, again associated with essentially, global conservation of mean momentum. These are upgradient eddy fluxes with respect to momentum. That is, this is not to be interpreted as eddies generated by an instability of the mean flow. On the other hand, it can be interpreted, as I will show in just a moment, as downgradient flux of eddy by eddy flux of mean potential vorticity. And so this brings me to the last slide. On the right, you can see a reminder of the shape of the ridge. This is not entirely the full domain. It's concentrated near the ridge. And what you see in the upper right are three different plots. One is in red, the eddy potential vorticity flux. In blue, the mean potential vorticity gradient with the sign change. All of this is vertically averaged over a deep layer with a mean temperature below 1.5 degrees centigrade, that is maybe in the bottom third approximately vertically of the domain. The ratio of eddy potential vorticity flux to the mean potential vorticity gradient is called the eddy potential vorticity diffusivity, as defined on the right side of the plot. And what you see is that the eddy potential vorticity diffusivity is essentially positive everywhere. That is, this is eddy potential vorticity mixing in the deeper layer of the ocean adjacent to the topography. And that is the mechanism of topographic turbulence, originally identified for barotropic flows and barotropic eddies, but here for three-dimensional baroclinic flows. If this were a purely barotropic flow, then if we were to come back to the Elias and Palm flux, the only eddy flux that would be allowed in a barotropic flow is the horizontal Reynolds stress. And you see that the horizontal Reynolds stress is playing a very important role in this 3D flow, but it's playing it mostly in the upper ocean where the eddies are strongest. And the potential vorticity mixing is near the bottom, where there is something closer to total potential vorticity conservation, but for the bottom drag, as opposed to the upper ocean, where the random wind forcing certainly makes potential vorticity non-conservative. This result, although it's shown for a particular solution with a particular set of parameters for stratification and topography and eddy forcing, is in fact a robust result of positive lower layer eddy potential vorticity diffusivity across many different solutions. This brings me to my summary. Using several different models and starting with topographic turbulence theory, regional simulations with very high mesoscale eddy resolution, full tidal forcing, realistic reanalysis forcing, and a parameterized bottom boundary layer is analyzed here in 4 basins. The only ones missing are the Arctic and the Antarctic Southern Ocean, which we have not ourselves done. Its time mean bottom slope currents demonstrate widespread topostrophic along slope currents consistent with the theory of mesoscale eddy rectification by essentially a geostrophic turbulence dynamics over topography. The bottom cross slope flow is mostly downhill, consistent with a one-dimensional bottom boundary layer of stratified topostrophic flow over slope, which is part of the Capo paper I cited earlier. But there are other regions with uphill flow, which in the terminology of mixing-driven circulation is referred to as diapicnal upwelling next to the boundary, associated with abyssal mixing, diapicnal mixing by deep inertia gravity waves and topographic wakes over a stratified flow without otherwise a mean circulation influence. Canyons and ridges give a complicated pattern of upwelling and downwelling as the topography goes up and down, into the canyon and over the ridge. They're evident in the complex flow patterns that are in the realistic simulations, although I only showed you the Mediterranean example south of Spain. And a idealized model of 3-dimensional baroclinic randomly forced mesoscale eddies above a ridge exhibits prograde downhill flow over the ridge consistent with the conception of eddy mixing of potential vorticity. I have presented here a sort of semi-global overview of the bottom current in the sense of trying to present the most common mean bottom slope flows, but there's great complexity in the patterns, which of course goes with a great complexity of the shape of the bottom of the ocean, all of which could be looked at in more detail. And one can even sort of imagine that there are therefore hundreds, if not thousands, of distinctive local stories that could be told. And what I have presented is in fact an overview. Thank you.
Thank you, Jim. Thanks so much. Very nice talk. So many new story, I think. And so we still have 20 minutes to ask questions. You can ask okay, you can send the message or ask directly. There is a question in the chart, I think.
Okay,
Can you see the?
I'll look in a minute. Do you still see my slides, although not quite so full screen?
We do not see your screen.
Okay, then you stop sharing, which is fine. So now I will go to the chat and try to read Chinese. No, that's just.
Can you see that? The recent
There's a question from
Yiwei.
Yiwei.
Yeah, from Yiwei, yeah.
Do you want to read it? You want me to read it?
Yeah, I read it, yeah. Recent numerical observational studies suggest that along slope flows aligned with the Kelvin wave propagation can drive downslope Ekman transport, injecting lighter water beneath denser waters and generating submerscale instability. Could the submerscale induced upwelling, maybe also a diabatic process, act as a key driver for the vertical transport of deep waters? Could you briefly explain the potential importance of deep sea submerscale processes?
Okay, the first part of the question is just a summary of my talk. So thank you. The middle part is asking about submesoscale instabilities. And I have shown no submesoscale instabilities. At the Mediterranean solution, it does have some submesoscale resolution in the 3 basins, and in the idealized problem, there's not quite submesoscale resolution. Topostrophy and downhill flow is mostly driven by mesoscale eddy, potential vorticity mixing. There is certainly the possibility of submesoscale instabilities, but not shown here. There are currently ideas about the baroclinic instability of the bottom boundary layer, which are based on idealized models. This is not what we've seen, even when we have submesoscale resolution in the Mediterranean. The importance of the submesoscale in all this is that it's a strong agent of dipycnal mixing in the deep ocean. And dipycnal mixing is essential for the bottom boundary layer, and it can even be important above the bottom boundary layer, but still close to topography. The usual ideas are that the submesoscales in the deep ocean are generated either by inertia gravity waves, many of which are generated by tides, or by submesoscale wakes, where you generate vorticity and flow along the boundary, which then separates and is unstable and induces a turbulent cascade and dipycnal mix. These processes are all important for water mass transformation. What I've been showing here is, call it a widespread local view of water mass transformation, because you cannot have flow across density surfaces unless you also have mixing. And so obviously we have mixing in these solutions. But this is not a picture yet of the global thermohaline circulation. The fact that W may be most often negative near the bottom slope may make a contribution to the global sinking, locally as a remote effect of the deep water formation. But obviously, on average, there has to be global rising and transformation of heavy water to light water. And our statement is this is not happening right next to the boundary. But obviously, it is happening other places, including fairly close to the boundary, but quite possibly other abyssal places as well.
Yes, Jim. So thank you, Jim. We have another two questions. One question is from Xincheng Zhang. He said, "Hi, Professor Jim McWilliams. Thanks for your talk. I noted in your paper you mentioned that the Neptune effect. Can you explain it in more details? Why call it a Neptune effect? I think does this effect need to parameterize in the models, ocean models?"
I never called it Neptune. Greg Holloway called it Neptune. But Neptune is in effect the same thing as eddy-driven topostrophy. It has sometimes been parameterized in global ocean models. Most of the parameterizations were in fact proposed by Greg Holloway, but they are barotropic parameterizations, which is not consistent with what we're seeing. And at the moment, there is no new parameterization of the topostrophic or Neptune effect used in non-eddy resolving models. In eddy resolving models, of course, you don't have to parameterize it. You calculate. Next.
Next, and I think this Jad Leaf, I think maybe a student from our university. Professor McWilliams, is your mean current Eulerian or Lagrangian mean? It is important for waves mean flow. Waves mean flow. It is important for eddy-driven mean flow. I think it's the answer. It's important for eddy-driven mean flow. So
well,
maybe the first question, Eulerian or Lagrangian mean?
Everything I've shown is Eulerian mean. Some of the theories of eddy mean interaction are Lagrangian mean theories, although they mostly refer to things like inertia gravity waves rather than mesoscale eddies, but there are Lagrangian mean theories for mesoscale eddy interaction. But as far as I'm aware, no one has ever considered topographic effects in such theories. The theory here is an Eulerian time average theory.
Mm-hmm. Yeah, so everyone, you can also open your microphone to ask Jim a question directly. I see there are also some international colleagues working on the similar topics.
Oh, Jim, may I ask some questions? This is Yusuke from Japan. Hi. It's quite challenging for us to look into the deep current by using ROMs. My question is very technical. And you said that the high vertical resolution is necessary to do so. And probably you use the bottom KPP as the bottom boundary layer representation. So could you give us any idea how fine our vertical model resolution should be, or how we should consider about the bottom boundary layer mixing parameterization in order to get the right answer for the entire ocean circulation energy budget?
Let's imagine for today that this is the right answer. What we do, ROMS is a terrain following coordinate, meaning it is extending from the bottom to the free surface. And we use a technique called vertical grid stretching which gives us relatively higher resolution in the surface ocean and in the bottom. And that allows us to resolve to some degree with scales of multiple meters the structure of the boundary layers as parameterized, and we use the K-profile parameterization that Jiwei mentioned in the introduction. Other people, of course, use other turbulence parameterizations. My general view would be that they will all give similar answers, but certainly not identical answers. I mean, parameterizations, well, what's the phrase? All parameterizations are wrong, but some are useful.
No, I'm not blaming anything about bottom KPP. I love it. But another question is
We're
that
typically using about, in these solutions, most of them about 100 vertical levels.
100 vertical levels. So would you say that if we would like to do the basin scale circulation correct, then we need a 100 vertical grid resolution with ROMs?
That's easy for me to say.
Okay. Yeah, thank you very much for your fantastic talk. I learned a lot. Thank you.
You're
Other
welcome.
questions?
Hi, Jim and Do. I want to ask.
Are you sure you don't want to walk across the building?
Yeah.
Yeah,
Yeah,
sorry, excuse me. Do you are in the James groups now?
No, I'm in the Daniel Lee Bench's group, but we are in the same office with James
Oh,
group.
yeah.
Yeah.
So UCLA.
Yeah, I'm now moved to UCLA now.
Okay, yeah.
Yeah, I have a short question. Maybe could you elaborate what determines whether it is mixing driven upwelling or it is eddy driven topography induced downwelling in the global ocean, and which one is more important for the abyssal mixing?
It's a competition, at least compared to the two conceptual models I presented. The topographic turbulence dates from 1976 to 1977. Interestingly, the mixing-driven bottom boundary layer dates from two papers in 1970, one by Owen Phillips and one by Carl Wunsch, which have then become more popular again in recent years as microstructure measurements have shown strong abyssal mixing. It's a competition. In different places, one will be more dominant compared to the other. And one can certainly imagine, hybrids of them.
Yeah.
The statement I'm making today is that the flow right at the bottom is mostly downhill. But there are certainly places where it is uphill. Excuse me, we're having a helicopter. What matters for the global ocean is the abyssal water mass transformation. And that doesn't happen just right at the boundary. And so, other than what I just said, I don't know the answer to your question.
Yeah, but still it helps a lot. Thank you.
Okay, other question? Jim, so I have a couple of questions. So you have the random eddy forcing, excuse me, the numerical simulations. So, but in the real ocean,
In
many
the
eddies,
idealized simulation.
yeah, idealized simulation. In the ocean, real ocean, many massive eddies are baroclinic. The signals cannot reach the bottom. Of course, some of the eddies can influence the bottom. So, what's your idea about the eddies in the real ocean for the eddy-driven mean flows in the
Well,
bottom?
eddies in the real ocean are mostly driven by instabilities of larger scale currents.
Mhm.
The most important of which is baroclinic instability.
Yes.
But eddies do reach to the bottom almost everywhere. They are surface intensified usually, but
It because of barotropization?
no, if let's do a GFD problem here. If you take a purely baroclinic mean flow and calculate its baroclinic instability, it will be partly barotropic, even in the instability mode, even without any inverse cascade towards more energy in the barotropic mode. So eddies are in the deep ocean. In some stories, mesoscale eddies were originally discovered by very deep floats that didn't hold still the way they were supposed to. They saw, eddy flows in the abyss. They didn't see the mean thermohaline circulation. So yes, in the idealized problem, the eddies are forced the wrong way, but still they're eddies. And they
Yes.
make apostrophe. And in the realistic simulations, the eddies, which are driven mostly by mean flow instabilities, mostly in the upper ocean, are still the cause of the topostrophic flow at the bottom or in the deep ocean.
So Jim, another question. So for the eddy-driven mean flow and also the downhill Ekman transport, you mentioned mostly adiabatic, right?
No. I mean, eddies are mostly adiabatic. The bottom boundary layer is diabatic. If we would go back and look at that Mediterranean cross-section of the vertical velocity and the buoyancy contours, you would see the downhill flow is crossing buoyancy surfaces, and that has to be a diabatic process on average.
Oh, so you mean your downhill flow includes both adiabatic and adiabatic components,
Yes.
right? So
The
it's
downhill
important
flow,
for
yes. The downhill flow in the topostrophic theory is a mixing driven or a mixing enabled cross slope flow, whether in the bottom boundary layer or a bit above the bottom boundary layer if there's, inertia gravity wave mixing or something like that.
So I mean the mixing, the mixing is isopycnal mixing or dipycnal mixing? Both or both?
Well, to cross isopycnal surfaces, water parcels must experience diapycnal mixing. So this picture of downhill flow, or even the mixing driven upwelling picture, all require diapycnal mixing mostly by flows that are smaller than mesoscale eddies.
So yes, thanks for your answer. So in the in our recent observation, actually I discussed with you in the email. In the South China Sea, we have in the deep basin, deep ocean, more than 2,000 meters deep. There is a cyclone circulation, a bit of circulation. Transitionally, we also observe deep western boundary current along the deep slope. Traditionally, we think it's the deep current is the western boundary current of the cyclone circulation. But after your talk, I think maybe we also observe many deep eddies. They do not have signal in the upper ocean at the surface. We cannot see in the altimeter data, but very from upmooring, very energetic in the deep ocean, more than 2,000 meters. So I'm wondering whether the observed mean along slope current, also driven by eddy, not by the traditional classical basal boundary western boundary current.
Well, you need something to drive abyssal mean currents. And if it's not thermohaline, then it most probably is eddy driven. And a cyclonic circulation in the basin of the South China Sea would be topostrophic.
Mm-hmm. Yeah. So our observation is a summit scale resolving 1.5 kilometer distant between two moorings. So we also observe energetic summit scale in the deep boundary layer in the on the slope. So the eddy induced vertical buoyancy flux is upward. It's also important for the boundary layer. I think the buoyancy bodies, but I'm not sure what's the role in the thermohaline circulation.
Well, I don't usually think of the South China Sea as a primary thermohaline pathway, but maybe it is.
Yeah, there are deep water flowing from the Luzon Strait into the South China Sea.
Okay, well then it may have
massive drop.
Okay. All very interesting, and we could talk in more detail.
Yes, yeah. Okay, so any other questions? It's still already 1 hour. Okay, no question. So Jim, it's 1 hour and it's late for you. I think maybe you should go back to take dinner. So thanks so much for your nice talk. We can discuss more details in the email, and in the near future, I think if you would love to, we want to invite to visit China, visit Ocean University of China in person. Thank you so much, Jim.
Goodbye.
Goodbye. Bye-bye. Goodbye, everyone. Thanks for your attention. Goodbye, Yusuk.